Okay, I know in the last talk, we're nearly there. Thanks to the organizers for having me. I'm really happy to be here. So I'm going to give quite a future-facing talk today. So I was driving down here from Livermore. I was kind of thinking, what do I want to communicate? What are my goals? So there's been some, really good talks that have done analysis that have heavily relied on Gaia astrometry. So I kind of want to reach those people. Roman, although not designed to do astrometry, is going to be an incredible astrometric observatory. So I want people that have, used Gaia data and relied on Gaia astrometry to start thinking about Roman. The launch is around the corner. It's next year. And more broadly, I want to reach people in general. The data is going to be public. There are not enough microlenses to analyze the data. So we need more microlenses. So hopefully, I can persuade people to get interested in microlensing for Roman. So I'm going to talk a lot about simulation work, and I'll give a shout out to my collaborators quickly. So this is people at Livermore that have passed through Livermore, and some people in the audience from Berkeley, Carnegie. So I realize that I'm the microlensing isolated black hole warm-up act. I think all of the talks are tomorrow. So I know there's not a lot of microlensing people here. So to kind of relieve my fellow microlensers of having to describe some of the basics, I'll quickly go through them. So when a lens gets between you and a distant background source, let's try the pointer. There we go. The gravitational field of the lens deflects the light from the background source. And this can give rise to two effects, right? So light that would normally come over here actually gets bent around and makes it into your telescope. The background source appears to get brighter for a short period of time. Because the light ray is bent, the source also appears in a different position for a small amount of time. This is astrometric microlensing. So when you've heard about microlensing, you've probably heard about the photometric side of it. Only recently has the astrometric side really been, coming to light and done really good things. So I'm going to actually talk a lot about the astrometric signal and not so much about the photometry in this talk. So this is a good picture to have in mind when you think about an astrometric microlensing event. So the white object is the lens here. It comes by. It lenses the background source. So you can see the background source here does this deviation as it gets lensed. So for people who want to think about the geometry here, this is just an elliptical deviation. And the kind of offset between the source and its unlensed position is always in this direction of the lens source separation vector. So although these two effects, come from the same underlying gravitational lensing phenomena, they're actually quite different in how they behave, how they manifest, what you can learn about the lens. So for the photometric effect, for a typical lens source in the galaxy, these events last days, months. And the nice feature of this effect is if you, get a really close lens source separation, you can actually bring your lens and source really close, and you can almost arbitrarily increase the amplification of your event. So this is why this effect is good for finding planets. So you can't bring it, this doesn't go forever, this eventually gets washed out by finite source effects and other higher order effects, but this means it's very sensitive to small masses, and you can find planets using this. And the signal is actually peaked when the lens source are on a closest separation. So the astro signal is a lot different. It actually is a lot less sensitive to the lens source separation. These events last a hell of a lot longer, so from the bottom end to months to even years to even decades in some cases for massive black hole lenses. And it's not like the photometric signal. You can't just get your lens and source closer and closer together and increase your amplitude of your offset. It's actually fundamentally limited by the angular Einstein radius of the system. And that parameter gets bigger when you have more massive lenses that are closer by. This is actually good for close by massive things like black holes, for example. But you can't just get these insane amplifications where you're very sensitive. You really are limited by how massive and close by your lens is. And the interesting thing is it's not actually temporally co-located with the photometric peak, so you can have events where you get the photometry and the astrometry together. The astrometric signal actually peaks before the photometric peak and afterwards. So this creates like a nice follow-up synergy, right? You've got two signals with different information contents, and you can see one first, the photometric peak, and then go after the astrometric peak after you've seen the event photometrically. So this creates nice time domain inference problems and strategies to follow these things up, which I'll talk about. So yeah, I mean, where microlensing shines, right, is we can probe the population of dark and isolated objects. Don't need a companion, don't need any flux from the lens. We're sensitive, right? So what people typically do, you run your microlensing survey, collect a sample of events, you measure something about those events, typically the time scale, the Einstein time scale, how long this event is, and that's loosely coupled to the mass of the lens. So then you can back out some distribution of how long these events are. And then if you're prepared to insert a galactic model, you can back out physical things like lens mass distributions. You also get interesting velocity information. So the events in the time domain, you get a snapshot of the relative lens source velocities. That means you're sensitive to things like kick distributions. And yeah, it's really the only way we can detect these things. So obviously, right? I mean, we expect the majority or the vast majority of black holes to be isolated, and we're kind of very biased to detecting things in binary systems, right? So to understand the full picture, we kind of have to understand our isolated population. It's very important. Maybe I'm stood too far away. There we go. So how do we currently find? So we found one black hole, right? Casey's here, and also the people that are involved. But we've been running microlensing surveys for about 30 years. About 30 years since the first microlensing survey. We've probably detected 20,000 events, microlensing events, over the course of those 30 years. A priori, if you run your galactic model, you expect about 1% of microlensing events to be caused by black holes. So why have we only found one? We just found the one. And that's because it's really hard to do it with photometry only. So typically, you know how the first one was found, and the strategy that people generally use, right? You have a large microlensing survey like OGLE, you have to monitor hundreds of million stars in the galactic bulge. That gets you thousands of microlensing events. You then select events that you think might be black holes. So you say, okay, events caused by massive lenses are likely to have longer time scales, so I'm going to make some cut on time scale. And then what you have to do to confirm the nature, to get more information, you have to allocate some incredibly limited, expensive ground space-based follow-up to confirm that the lens is a black hole, weigh it, look for excess flux. And yeah, so this is the current way that we're doing it, and we're entirely limited by the astrometric data that we have available. And it's just hard to find events if you start off from a ground-based photometric survey. So I'll try and explain why. So this is a plot. If you run a galactic simulation and you run a simulated microlensing survey and you plot where the stars, white dwarfs, neutron stars, and black holes end up in the observation space. So this is the Einstein timescale. This is basically how long the event is. This is proportional to the square root of the mass of the lens. And then you have this other thing called microlensing parallax. So because we're on Earth, we're accelerating. As we move and observe the event, this kind of distorts the light curves. This is like a kind of extreme distortion of the microlensing light curve due to parallax. And this tells us something about the relative lens source distances. So this is basically the lens source parallax divided by the angular Einstein radius of the system. You see that the different lens classes separate out in this space, right? So what you're seeing here is you're just seeing separation in mass, basically. So mass brings you this way. So the more massive things, the black holes, are down here. The less massive things are this way up here. So this is great, right? You see that the black holes are kind of separated from your stellar lenses, so it should be easy to select them, right? It's not. So the typical parallax constraint you might get from the ground is large. So imagine trying to, decidedly put something here with an error bar like that. It's kind of really hard. And this is fundamentally because the black holes have a low signal in the pi space. This is a low signal to noise part of the parameter space. So black holes don't look like this at all. They're not extreme. They basically look like normal symmetric events with a tiny or no deviation. So you're looking for the absence of a signal to find your black hole, which is really hard. So if you actually revisit the one that we did find and put it back in this space, so instead this space is like that scatter plot that I just had on the previous slide, but instead of the scatter plot, I've actually now built some probability surface. So this is the green regions are the regions where we expect the black holes to be, and the blue regions are the regions where we expect the white dwarfs to be. So this takes into account the shape of the scatter plots and then corrects for the relative abundance of each of the classes of lenses. And you can see if you look at the posterior distribution of where the isolated black hole candidate lies, it actually is a lot more consistent with being a white dwarf, right? I'm not saying it's a white dwarf, it's definitely a black hole. But what this is saying is that, you know, if we'd have thought carefully about this and maybe trying to allocate expensive follow-up was kind of a high-risk strategy, right? This is, if you just look at the light curve, this is, you know, much more likely to be a white dwarf than a black hole. And, you know, nobody's doing anything intrinsically wrong here. This is just because it's really hard to measure anything robustly down here. So, in fact, you know, the one that we found was part of a larger sample, and all the rest of them didn't turn out to be black holes. Okay, but we're fundamentally stuck, if we just start with ground-based photometry, looking in this region where we turn over quickly from things being black holes to being white dwarfs or stellar lenses. This is like a fundamentally hard place to look for black holes because it changes very quickly. And we're kind of stuck here with photometry. So yeah, incredibly high risk, but I think we got lucky, really. Okay, I think we've stopped working. Okay, good. It's not going. Are you able to exit out of that? Oh, it's this. Oh, the VPN's come for me. Hang on. Oh, good. Okay, good. Great. Okay. Oh, man, has it come again? Oh, good. Okay, great. Okay, things are changing, though. We have these amazing astrometric observatories, right? Gaia's just finished this decade-long astrometric survey of the sky. We've got Roman, that I'll talk about in a minute. We've also got HST, James Webb, and Euclid as capable astrometric observatories, right? My point is, I don't think it's going to get better than this ever again. We've got these amazing astrometric observatories abundantly available, and there's this, you know, there's this rich data that we can really take advantage of. So Roman's going to complete a galactic bulge time domain survey. This survey is not for astrometry, it's not for black holes. This is to take the demographics of microlensing photometric exoplanets. But if you take a step back and just assess it as an astrometric survey, it's actually quite good. So these numbers have changed, they've been updated since I wrote this slide, but they're roughly correct. So it's going to survey about 2 square degrees of the galactic bulge for about 5 years. There's going to be these high cadence 70-day seasons where we're going to take observations every 12 minutes now. I think it's gone down from 15. And there's going to be these lower cadence seasons in between. And so if you like compare it to Gaia, for example, so Gaia's got a lot more stars, it's all sky, right? We're a lot more tiny. But if you look at like the kind of astrometric precision per epoch, so if you stack Roman data over a 24-hour period, we expect no real astrometric changes, and then you compare that to one of Gaia's observability periods for a source for something that's well exposed. Roman's actually right down here in this novel place, right? We've got loads of epochs, and we've got a really good per epoch astrometric precision. So it's a really good transient astrometric machine, which is kind of exciting. But yeah, I think the kind of where it suffers, right, is the number of sources in the sky coverage. It's a tiny patch of sky. So what does this do for microlensing? It actually opens up a whole new channel. So the whole galactic bulge time domain survey for Roman is focused right here. Just photometry, finding exoplanets. We found the first black hole with this, photometric on the ground, astrometric from space. Roman's actually going to find events that are so widely separated that they just have an astrometric signal. So there's going to be things that are missed by any kind of photometric alerts that are just these astrometric anomalies that appear in their data stream. And there's going to be a lot of them. And so you get more information when you have the astrometry. So when you have the astrometry, you get to measure the angular Einstein radius. So if you remake these plots, for where your lenses end up, your stars, your white dwarfs, your neutron stars, and your black holes, and you look, instead of in the photometric space, you look in the astrometric space, your black holes end up away from the main population, great, but they also end up in the high signal-to-noise space. So these are larger theta E's, these are larger astrometric signals, these are easier to measure. Same with TE. So this is a typical kind of constraint you'd get from galactic bulge time domain survey on theta E. You can see that we're going to be able to basically confidently identify black holes with the astrometric data, which is much better than we could do with the photometric data. So we ran loads of simulations. So Jessica's, I think, going to talk about this tomorrow in detail. I'll just briefly run through it. So we did a lot of simulation work at Livermore. So we used Popsicle, you basically build your model of the galaxy, you go through stellar evolution, you create your black holes, you run your simulated microlensing survey, and you get out this catalog of simulated events for survey parameters and whatever. And here's some of the knobs you can tune on that simulation, but I think Jessica's going to talk in detail about this tomorrow. So we run all of these simulations to find out, what Roman can actually do and what we can detect. And so here's some of the astrometric tracks of these astrometric microlensing events. So actually quite surprising, so maybe not relevant to this conference, but you can actually detect things down to Jupiter mass in these astrometric tracks that are going to lens something, which is, I think, kind of insane. But as you see, as you get towards things that are kind of black hole mass-like, you can see these red dots here are surveys, seasons of the Roman galactic bulge time domain survey. And these green tracks are the deflected signal, and then you've got the blue tracks, which is the unlensed signal. So you can see that, as your events get longer, you get more of your data is these astrometric accelerations from the microlensing. So the actual limit on what Roman can do as an astrometric survey for finding black holes is not limited by the precision cadence or anything like that. It's actually limited by the duration of the survey. So there's a lot of astrometric microlensing that you can see down here, right? You're almost all signal at this point through the full 5 years. So you're actually limited by getting a detectable change in the astrometric signal within 5 years of the survey. So that kind of cuts off the massive end of the mass that you can probe as a lens. But there's going to be many things from 1 solar mass to 10 solar mass where we'll clearly be able to see the astrometric signal in the data. So if you just run basic yield calculations, so these are the things with just astrometric signals, wide separation lensing events, expect about 330 black holes, similar number of neutron stars. And this is exactly the same as you'd expect where you get these closer in events that have both astrometry and photometry. So this is going to be, in terms of numbers and information content, as important as the kind of well-studied way to get microlensing events with Roman. So I'll mention this for neutron stars, but you can play the same game with black holes. So again, we're in this astrometric signal space. So we've got T of the event, theta E of the event, which you measure with the astrometry. If you tune up your kick distribution for your neutron stars, you can move the population of neutron stars out of the bulk of the population. You can't do this in the photometric space. What does this mean? It means that depending on the kick distribution that you get with neutron stars or black holes, you will get events that are uniquely identifiable as neutron stars or black holes. And depending on how many are here, we'll be able to probably constrain the kick distributions with these measurements, which is exciting, I think. So yeah, this is just same point. Photometric space, this is the probability surface. Anywhere green, we can find something that is high confidence, not a black hole, neutron star, just stars. This is anything purple. This is a region where we expect neutron stars to be uniquely identifiable. With just photometry, we can't find any neutron stars. With astrometry, we can actually begin to find them, which is kind of exciting. But you can play the same game with black holes up here. Yeah, so I'll just plug the software that we made to do this. These simulations that we ran lots of versions of simulations, about 10 million core hours at Livermore. We have plenty of compute to spare there. So we basically, made this into a software package so people can take the Roman data, take the posteriors of their event, and try and classify and find black holes pretty easily. It's very fast to run. This is Greg Salary that led this. So yeah, there are challenges, right? So I've gone through all of the good things about Roman astrometry, but careful, precise astrometric processing is actually not within scope for the Roman survey at all. It's going to be an incredible astrometric machine, but there's no kind of penciled effort in the Roman collaboration to do this work. So the microlensing pipeline is going to produce basic epoch astrometry. But it's not going to do, it may do, but it probably won't do stuff that is good enough to detect most of these astrometric anomalies. And there's going to be hundreds of black holes in there, isolated, that we're not going to see if we don't do the astrometric processing. And as well, I've just mentioned, so Gaia got very close to doing this. So Gaia had photometric alerts. So obviously the per epoch astrometry for Gaia is coming, is it next year? Yeah, probably sometime next year. So they had a program, the Photometric Science Alerts, run by Łukasz Ronankowski and Simon Hodgkin out of Cambridge. And this was this transient part of Gaia where they were allowed to, say if something was photometrically varying in the data, they could publish to the community. They got very close to doing this for the astrometry as well. So they got very close to saying, hey, we can say that there's something that's astrometrically behaving anomalous. But they didn't get the funding to do it or the support. With Roman, there's a chance to do this, right? There's a chance to actually monitor and alert on the transient astrometric sky for the first time, which I think is really exciting. And of course, I'm just talking about microlensing here. I haven't mentioned astrometric binaries. There's probably going to be loads in Roman. Okay, I'll just leave my summary up there, and I'll take questions. Thanks.
And the speakers are more than on time, so I really don't have to do anything. This is great. So questions for Peter? I see a few right now. Kareem, why don't we start with you?
Thanks. Could you talk, is there a degeneracy between interpreting an astrometric signal as due to microlensing or due to a binary? Especially if there's no accompanying photometric signal, and can you break it?
Yeah, good question. Yes. So I think the area of concern would be the events caused by, masses that are 2, 3, 4 solar mass black holes. You're going to see basically all signal over the 5 years, right? And who's to say that that isn't all signal of some slowly varying astrometric binary as well, right? So there probably is ways to break the degeneracy, right? Parallax might help you out a little bit. Yeah, I'm not sure. I think the microlensing signal is a lot more non-linear in the acceleration compared to the astrometric binaries. There's very fast changes towards the peaks, and then it goes very slowly. So maybe in the higher derivatives, possibly, but yeah, I haven't looked at breaking those degeneracies.
All right, thanks.
Hans-Walter Rix, MPIA Heidelberg. Of the numbers you have up there, the 600 and 430, how many of those do you think the Roman data alone, photometry plus astrometry, will allow you to do an unambiguous assignment that it's a black hole? And if so, in the other cases, is there external data that can help you gain confidence?
Yeah, it's a good question. I imagine, yeah, I don't have the exact number on that, but I think for a lot of them, if you have the photometry and astrometry, that means you have DTE, TE, pi-e, that means you can probably get a mass. And then if you can, we're going to get, be able to do quite precise kind of analysis of the lens flux. So you can probably rule out that it's a luminous lens, but this is configuration dependent. So for probably quite a few of them, but for not all of them, it's geometry and event dependent. But I would say to actually learn about the population of objects, you don't actually need to do this. So we developed a framework where you probabilistically assign lens classes based on the characteristics, and you actually don't need to know the class of any lens with great certainty to marginalize over that and get a constraint on something like the mass function of black holes. you can model everything jointly and it works.
Sorry, if the black hole was a binary, can you tell?
I mean, the astrometry is going to help. I think Jessica wants to answer.
I'll show you some tomorrow.
Yep, okay. Yeah, the astrometry is really good for breaking binarity conditions, so you can have a lot of work that Natasha Abrahams has done. There's microlensing events where the photometry looks identical to a single lens, but if you look at the astrometry, the astrometric signals of those events are very different. So there's degeneracies you can break by the astrometry only.
Okay, Przemek Mills, University of Warsaw.
Hello.
So Raman will observe very densely, so it will observations every 15 minutes for 6 months, then there will, for 6 weeks, then there will be a gap, which is 6 months long, and then you will have another bunch of very dense observations. Is there any plan to fill in the gaps? And if not, how would that affect the ability to detect black holes with Raman?
There's definitely plans to fill in the gaps. Jessica's leading those efforts. I think she'll talk about them tomorrow. Yeah, with returns to how that affects the signal, for black holes, the events are really long. They span multiple seasons. The astrometry falls off very slowly. So unless you're relying on the photometry, then perhaps, but if it's just astrometric only, and you're deriving all your information from the astrometry, I don't think the gaps are a huge problem.
Except for binaries.
Sure, binaries. Yeah, all of this work, I didn't put in the binaries into the simulations. So the caveat of most of this work is that I've only assumed single lenses, and of course we know that there's lots of binaries out there, so binaries do complicate things.
Adam Burrows, I've been looking forward to your talk all week, and it didn't disappoint. That's quite a good number. I'm interested in how well you might, at least collectively, astronomy, using these data, be able to get the velocity distributions of neutron stars, get a correlation between the velocities and the masses, and similarly for the black holes.
Yeah, I haven't done the calculations about the constraints you could get precisely. But I mean, just going on the numbers that we expect, we're going to get a really good estimate of the number of isolated black holes for sure. With the kicks, going back to, if it'll let me go back. Going back to this, right, when there's going to be a large signal here, right? The kicks do something to the neutron stars and black holes in the astrometric observable space that doesn't happen in the photometric space. So I have high confidence there's definitely going to be some kind of constraint we can derive. I can probably do the calculation, I just haven't done it yet.
Okay, what I'm referring to again is kick mass correlations.
Kick mass. Yeah, I haven't thought about it. I'm sure you could model them jointly. It's probably going to be hard though.
Certainly statistically, I think you can extract something. Anyway,
yeah.
I would encourage that.
Okay.
More questions?
Sorry.
The simulations you've done, how much have you taken into account the fact that the galactic bulge is going to be very crowded in the infrared band?
Sure, yeah. Yeah, we're assuming that for the detectability cuts of the events, right, it's going to be hard to do astrometry in the bulge. It's crowded, blended, it's going to be terrible. So Gaia, an aside, right, is that this data set is going to be basically complementary to Gaia, right? Gaia can't see the highly extinct stuff, and it also does incredibly poorly in crowded regions. So back to your question. Yeah, so in the detectability cuts, we only picked sources in the simulation that were highly unblended and not directly crowded with other sources. So this is kind of like a pessimistic yield. I'm sure we can do something with deblending sources that we haven't looked into. These are pessimistic if we're picking things that we know are not blended, not overly crowded. So yeah, they have been taken into account.
Hi, fantastic work. Just Tomer Shanar, just a brief question to make sure I get it straight. So Roman, what would be the ratio of astrometric wobbles coming from binaries compared to microlensing events?
I don't know. I haven't done that calculation.
But do you feel like the binaries are going to dominate this signal, or not necessarily?
Do you have an idea, Kareem? In case he did, yes, Casey did some simulations as well.
It's coming.
I remember.
Thanks. I guess I attempted to simulate it, and a very rough forecast is like maybe 200 astrometric wobbles in Roman. So of orders similar to
Yeah.
Gaia, probably. Black holes. Total. Okay, I did not calculate that.
Yeah.
It's related to this.
So, so Teja here. So, lensing is achromatic.
Yes.
So, you would not see the RV perturbation that a binary would have. So, just saying that.
Go ahead, Kareem.
Yeah, I mean, just remember, order unity of stars have a binary at the relevant companions, and I think the scale of, like, most of the signals you showed kind of have curvature on the time scale of Roman, so you're sensitive to periods of few years to a few decades.
Right.
And I think, you just put the companion farther and farther away, and the binary signal gets bigger and bigger.
Mm-hmm.
So I think, I actually didn't realize until your talk that you could have astrometric only candidates to begin with, but I think definitely in order to sift through the much larger sea of binaries will take a lot of work.
Yeah, for sure.
Look at the middle right panel. That's the 10 solar mass black hole. And you get a baseline in there too. It's a pretty dramatic condition. I think those are harder to look like.
Yeah, I guess why is it that some of these, what is the blue line, like why is it that some of these have a lot of wiggles in the blue lines and other ones are almost straight?
Parallax. Distance to the lens, distance of the source.
Why should they say that the gaps don't matter? If I look at the middle right, it would be nice to have the gaps really.
The middle right.
Second row on the right.
Yeah, I mean, there's some. Well, what information do you get in the gap? What do you get that you don't get in the amplitude in the main part of it and off to the start? Sure.
Yeah, I mean, to me, if I look at the middle right, it's a big signal. But remember, with an astrometric binary, you get a bigger and bigger signal the farther away you put it. So I think if you just have a companion at,
No, it's parallax that'll separate them. So, yeah, astrometric microlensing is the only thing that can generate an astrometric signal on a source that is far away, right? So if you have a parallax of your source and you know it's very distant and it has this huge astrometric deviation, it can't be a binary, right?
Yeah, I mean, it can't be a binary with a low mass.
Right. Oh, sure, yeah.
Okay, thanks.
Other questions? While I'm bringing this to Tom, people are thinking, I do have one very naive question. If you go back to your plot that was showing the location of all the stars, white dwarfs, neutron stars.
This one or the earlier one?
This one is okay. Well,
okay.
Yes, yeah. So for these ones that kind of span the regime that's more polluted with these other, white dwarfs and stars, are there any additional things that can be done to help disentangle them? And what would that look like? Is it different telescopes?
Yeah. Lens flux analysis. So Roman's going to give us a high resolution view. We can actually see if there's a luminous lens hiding in there. If there is, it's not a black hole. But I must stress that to do the population analysis and constrain something like the mass function of lenses, you do not need to know with certainty the class of every event. You can marginalize over it and treat it probabilistically. You can do that. So you don't need to pin each event perfectly. As long as you have some tight coupling to the hierarchical model, which is very tightly coupled to theta e, you can still do the inference for the population.
Do we have any, I know you, Tom, any other questions? Great. Tom, why don't you close us out then?
Okay, yeah, so the parallax signal you get, is that going to be for the lens, for the source, or is it going to shift between the two of them as the event?
It's going to, you're seeing the source here, right?
Yeah.
So you're going to get the parallax of the source at baseline, but then the parallax motion of the lens, if it's really close, is going to imprint on the signal of the source, right?
Yeah.
So you're going to see, for lenses that are really close by, you're going to see some combination of, parallax of the source, then lens parallax of the lens imprinting it onto the source trajectory. But for most things, you're just going to see the parallax of the source and then some elliptical deviation on top of that in some random direction.
Okay.
All right, I think it's wine time. Let's thank Peter again and both of our speakers in this section.